All right, welcome to the deep dive, everybody. Today we're going to be looking into something really kind of mind-blowing. We're talking about AI, but not just the simple chatbots we see every day.
No, no, not at all.
We're talking about the big leagues.
Exactly. We're diving deep into how artificial intelligence is being totally transformed by these large language models, these LLMs you hear about. And what's really exciting are the agents they're making possible.
The agents, yeah.
These aren't just answering basic questions. We're talking agents that can reason in super complex ways,
Wow.
understand the world around them, and even take actions,
Yeah.
real actions, in all sorts of different areas.
It's like science fiction becoming reality.
It really is.
So for this deep dive,
Yeah.
we've gone through a ton of research, haven't we? We've got
We have. We've brought together all this knowledge about how our own brains work, the latest from neuroscience, and of course all the cutting-edge stuff happening in computer science.
It's a lot to process, but
It is.
what we really want to do for you, the listener, is like cut through the noise and give you those core insights.
Exactly. How are these intelligent agents actually built? How do we even figure out if they're good or not? And how are they constantly getting even better? We want you to walk away with that core understanding.
Yeah. Not get lost in the jargon.
Exactly.
And something that really blew my mind when we were going through the research was this idea that, to design these super advanced AI agents, they're actually looking at us,
Yeah.
at the human brain,
Right.
for inspiration. Like different parts of the AI are mirroring our own thinking.
Yeah, the way we sense the world.
And even our emotional responses, it's wild.
It really is. It's like they're trying to build a digital version of our own minds in some ways.
So let's break this down. If we're thinking about these AI brains kind of like our own, what are the essential parts they need to have? What makes them tick?
So, just like us, memory is absolutely crucial.
Of course, yeah.
They need to hold on to information and then be able to recall it when they need it.
Makes sense.
And our sources, they go into all these different types of memory in agents. And it's fascinating to see how they relate to our own memory. So you have short-term memory for what's happening right now.
Like holding a thought.
Exactly.
Yeah.
And then you've got long-term memory for more permanent knowledge.
Facts, experiences, that kind of thing.
Right. And then there's sensory memory for those initial inputs, like seeing or hearing something.
Like our senses.
Exactly. Then episodic memory for specific events.
Like remembering what you had for breakfast.
Precisely. And then there's semantic memory, which is more for facts and concepts.
General knowledge.
Right. And finally, procedural memory for how to do things, the steps involved.
Like riding a bike or something.
Yeah, exactly. And there's even an equation in our sources, equation 3.1, that tries to formally describe how all this raw information from the world gets turned into something the agent can actually use. And what's really cool is seeing how all these different types of memory are implemented in real AI agents. You've got a reagent, which focuses on remembering recent text, MemGPT for managing the flow of conversation, Aerograph for storing knowledge, AG for learning skills. It's all there in table 3.6.
So many different ways to remember.
Exactly. It's not just about having storage space, it's about having the right kind of memory for the task at hand.
Okay, so it's not just recording everything, it's like organizing.
Yes.
And accessing different types of information depending on what they're trying to do. What's next? What's the next big piece of this AI brain puzzle?
So after memory, the next crucial component is what we call world modeling.
World modeling, okay.
This is how these agents build up their own internal representation of the world around them. Kind of like how Craig talked about us having small-scale models of reality in our heads.
Like a mental map, right?
Yeah, exactly. It's like a mental map that lets them imagine different situations, reason about what's happening, and even try to predict what might happen next.
So they're not just reacting, they're thinking ahead.
Right. And our sources talk about 4 main ways agents go about creating these world models. You've got implicit models, where the model learns relationships in the world without directly representing them. Large language models themselves can often work this way.
Okay.
Then you've got explicit models, like Mu0 and Dreamer.
Specific examples.
Yeah, which actually learn a direct model of how the environment works, kind of like a physics engine in a video game.
Oh, interesting.
We also have simulator-based models, which rely on external simulations or even real-world interaction, like Sapien, which is used to train robots. And finally, there are hybrid or instruction-driven models that try to combine the best of these different approaches.
So it sounds like there's a bit of a trade-off here, right?
Absolutely. The big challenge is finding the right balance between how detailed and complex the world model is and how accurately it can predict what will happen. Simpler, implicit models might be easier to manage, but harder to fully understand, while more complex, explicit, or simulator-based models can be really demanding on computing power. And a really important point our sources make is that being able to link memory to these world models is essential.
Oh, yeah. Why is that?
Because you want those short-term predictions to be informed by a broader understanding of the environment, the agent's history.
Okay, that makes a lot of sense.
Just like you wouldn't want to make a decision based on just a snapshot of what's happening right now. You'd want to consider your past experiences as well.
It's like context, right?
Yeah, exactly. Context is key.
Okay, so they've got memory, they're building these mental maps of the world,
Yeah.
but what actually makes them want to do something? What's their motivation?
That's where reward processing comes in.
Reward processing.
Yeah. It's all about how these agents learn what's good, what's beneficial. And our sources draw some really interesting parallels between how AI agents learn through rewards and the reward pathways in our own brains.
I've heard a little about that, like dopamine and stuff, right?
Exactly. They even mention the role of dopamine in our sources. It's in table 5.1. But there's some pretty big differences too.
Oh, for sure.
We can program an agent's reward system to be super specific to a task,
Right.
whereas our own motivations, they're often much more complex and way less clearly defined.
Yeah, much messier.
Definitely. And when it comes to how AI agents are rewarded, there are a few main approaches. There are extrinsic rewards, which are directly tied to specific goals, like completing a task.
Okay.
And then there are intrinsic rewards, which encourage exploration and learning. Things like curiosity, as explored in the work by Pathak and others in the planned explore approach, or seeking out new information, like in CONINFO and VM. But there's a big challenge here, what we call reward misspecification.
That sounds tricky. What is that exactly?
It's making sure that the reward we give the agent actually leads to the outcome we want. You know, an agent might technically achieve the reward,
Right.
but in a way you never intended, and maybe even in a way that's harmful.
Oh, that's a bit scary.
It can be, and that's why a lot of research is focused on making sure the rewards are aligned with our values.
And another thing I thought was really fascinating was how our sources talked about emotions being incorporated into these LLM agents.
Yeah.
Emotion-like systems in AI. It's a wild concept. What's the thinking behind that?
The idea is that if we can give agents something akin to having moods or responding to emotional cues, it could actually make them more effective and trustworthy.
How so?
Well, think about it. If an agent can recognize and react to emotional signals in the environment, or even show consistent emotional states itself, it could lead to interactions that feel more natural and intuitive.
More human-like.
Exactly. It can make it easier for us to understand why the agent is doing what it's doing and even build a sense of rapport with it.
Okay, that's interesting. So we've covered thinking, and now something like feeling. But how do these agents actually take in information from the world around them?
That's where perception comes in, the sensory part of the AI agent.
Like our senses.
Exactly. And while we humans have our limits on how fast we can process information, AI often operates much, much faster, mainly limited by the hardware it's running on.
Oh, right.
And a really important area here is what we call cross-modal perception,
Cross-modal.
where agents can combine different types of sensory input,
Yeah.
like we do naturally.
So not just seeing, but also hearing and understanding those together.
Exactly. And there are all these amazing models being developed to make this happen. You've got Coclip, A-Line Jane, and Cyclip for understanding text and images together, AudioGen for connecting text and sound, Speech T5 for linking speech and text, and even more comprehensive models like ImageBind, PandaGPT, and NextGPT, which are all laid out in Figure 7.1 in our sources.
It's like they're trying to recreate all of our senses.
In a way, they are. The goal is to have a seamless integration of different senses, just like how we experience the world.
Okay, and it's not just about passively receiving information either, right?
No, absolutely not. There are ways to actively improve an agent's perception.
Like how?
Well, one approach is involving humans in the loop to provide feedback on what the agent is perceiving, making sure it's accurate.
Okay.
And another approach is using techniques to clean up the information the agent takes in, like filtering out noise, or to refine how it presents its outputs, making it more understandable to us.
Oh, interesting. So it's not just about the raw data, it's about making sense of it.
Exactly. And our sources also talk about how the complexity of the AI model itself, the difference between a smaller model and something huge like GPT-3 or Llama 3, and the power of the hardware it runs on, things like NVIDIA's H100 or RTX 4090, all play a role in how effectively these agents can perceive the world.
So bigger models and better hardware basically lead to more sophisticated perception.
In general, yes.
That makes sense. So they can perceive they're getting all this information from the world, but how do they actually do things based on all that input?
That's where the action system comes into play.
The action system.
Okay, this is how the agent actually interacts with its environment, makes things happen. And there are a few different ways agents learn to take action, according to our sources. One is in-context learning.
In-context learning.
Yeah, which allows them to quickly adapt to new tasks based on the information you give them in the moment.
Learn on the fly.
Right. Then there's supervised training, where they learn from examples of what to do in different situations.
Like training a dog, kind of?
Yeah, a bit like that. And then there's reinforcement learning, or RL, which is all about learning through trial and error based on the rewards they receive.
Ah, rewards, like we were talking about earlier.
Exactly. And there are different methods within RL, like DQN, PPO, and even specialized techniques like RLHF and DPO, which our sources go into.
Lots of acronyms. But it sounds like this RL is a powerful way to make these agents actually learn how to act in the world.
It really is. And it's not just being used to learn basic actions, it's even being applied to improve reasoning abilities, like in models like RivFT, DeepSeek R1, and K1.5.
Wow. And I notice our sources also mention tools.
Yes.
What's the deal with agents using tools?
This is a really interesting development, where the idea is to give agents access to specialized tools to expand their capabilities.
So it's not just about what's in their brain, it's about what they can use in the world.
Exactly. And these tools can be for very specific tasks, like scientific research, or they can be more general purpose tools. We see examples like Honeycomb, ChemCrow, SciTool Agent, and SciAgent, which show how integrating these tools can allow agents to tackle really complex problems in fields like material science, chemistry, and even broader scientific research.
It's like giving them hands to work with.
In a way, yes. It gives them the ability to manipulate their environment and accomplish things they couldn't do on their own.
It's pretty amazing to think about these agents not just as static pieces of software, but as things that are constantly learning and getting better.
It really is.
How does this self-evolution happen? What are the mechanisms behind it?
That's a really key question. And our sources point to a shift away from us humans manually designing every little detail of AI systems towards systems that can actually learn and improve themselves.
So more autonomous, more independent.
Exactly. And this is similar to the ideas behind AutoML and neural architecture search, or NAS, in more traditional AI. The benefits are pretty clear. Much greater efficiency, lower development costs, and a path towards intelligence that's more closely aligned with how intelligence evolves in nature.
So instead of us constantly having to tweak and adjust them, they figure out how to perform better on their own.
Right. And our sources explore different ways this happens, including something called prompt optimization.
Prompt optimization, okay.
This is where the instructions we give to large language models are automatically refined to get better results, using various techniques like OPRO, Protegi, TextGrad, and Revolve.
So it's like the instructions are being optimized as well.
Exactly. And then we can evaluate how well these optimized prompts actually work, based on things like how well they perform on a task, how efficiently they use resources, and even qualitative aspects like consistency and fairness. But it's not just about optimizing the prompts themselves, there's also workflow optimization.
Workflow optimization, what is that?
This looks at how multiple AI components within a system, like in MetaGPT or AlphaCodium, can be better organized and coordinated. It's about optimizing the connections between these different components using different techniques.
So it's like taking the individual optimized pieces and making sure they work well together.
Yes. It's about optimizing the whole system, not just the individual parts.
Okay, so they're optimizing themselves, their prompts, their workflows. But what about creating entirely new abilities? Can they do that too?
That's where it gets even more interesting, with the dynamic creation of new tools. Researchers are exploring how agents can actually generate new tools on their own, based on their understanding of the tasks they need to perform and how they're using existing tools. Systems like Toolmakers, Creator, and Craft are examples of this, aiming to make agents more adaptable and efficient.
So they're not just learning to use the tools we give them better, they're figuring out what new tools they need and building them.
Exactly. It's a pretty big step towards true autonomy.
Yeah, it's incredible. So how do they actually improve over time? What are the different learning paradigms?
Our sources talk about a few main approaches. There's online learning, where they learn from immediate feedback as they interact with the world.
Okay.
Then there's offline learning, where they learn from carefully prepared data sets kind of like study. And then there are hybrid approaches that combine both online and offline learning, as shown in Figure 11.1. There are also techniques like dynamic parameter tuning, like self-steering optimization or SSO, which allows agents to adjust their internal workings in real time.
Wow, self-tuning. That's pretty cool. And our materials also talked about agents actually generating and testing new ideas, like in scientific discovery.
Yes, this is a really exciting area where agents are being used to make autonomous scientific discoveries. It's all about generating hypotheses and then testing them, like the philosopher Karl Popper's idea of falsifiability.
Okay.
Systems like the AI Scientist Agent Laboratory in Genesis have already shown a lot of promise in areas like creating new types of images, understanding language, and even systems biology.
So they're coming up with research questions, running experiments,
Yeah.
even writing up their findings.
In some cases, yes. There are even examples of agents designing new materials and molecules like LO-MAT design and ChemoS 2.0. While they still have some limitations, especially with complex math and symbolic reasoning, using external tools often helps them overcome these hurdles.
It's pretty amazing to think about AI not just working on its own, but collaborating and evolving together.
It is.
And that's where multi-agent systems, or MAS, come in.
Yes.
What are the core ideas behind these systems of multiple AI agents?
The foundations of MAS actually draw inspiration from natural systems, like biological ecosystems
Oh, interesting.
and human societies, looking at ideas like the wisdom of crowds, Minsky's concept of a society of mind, and the importance of understanding other perspectives.
So it's like they're trying to recreate those dynamics in AI.
Exactly.
Mhm.
And the core idea is that by having multiple AI agents working together, we can potentially achieve things that a single agent could never do on its own.
Okay. And are these agents all the same, or do they have different roles?
They can be either.
Mm.
Homogeneous agents are pretty similar to each other, while heterogeneous agents can have different roles, abilities, and ways of interacting. Our sources categorize how large language models are being used in MAS along three main lines. Strategic learning, like in economic simulations and games, creating models and simulations of agent behavior, and collaborative problem solving.
So it's kind of like building AI teams with different specializations, right?
Precisely.
Yeah.
And when you're putting together an AI agent team, you can have diversity in terms of their persona, like what kind of personality they project,
That's cool.
their capabilities, what specific tasks they're good at, and their action space, a range of things they can actually do. Think about the different roles in a game like Werewolf or robots with different physical abilities.
I get it. So how do these teams actually coordinate and communicate?
That's where agent interaction protocols come in. These are the rules that define how agents talk to each other, including the types of messages they exchange and the interfaces they use. Systems like SciAgents, MetaGPT, and AgentBench all have their own protocols. And newer protocols are exploring things like identity, negotiation strategies, flexibility in communication, and how centralized or decentralized the communication is. All of this is laid out in Table 13.1 in our sources.
Lots of different ways to communicate.
Yeah. And the overall structure of the system, whether it's fixed, like in Medeco, or dynamic, like in Dylan and GPT Swarm, also plays a crucial role.
Okay, so we've got the communication protocols, the structure, but how do these agents actually work together in practice? What does collaboration look like?
Our sources describe different ways agents can collaborate. There's consensus-oriented collaboration, where the goal is for agents to reach an agreement, as seen in the agent laboratory.
Working together towards a shared goal.
Exactly. Then there's collaborative learning, where agents share their experiences and learn from each other. This can happen through direct experience sharing, like in MES-CTC, or through peer discussions, like in Medeco.
Like a study.
Yeah. There's also observational learning, where agents learn by watching what other agents do, as in Agent Court and iAgents, and even teaching and mentoring interactions, where more experienced agents help newer ones learn. And ultimately, the goal is for this collaboration to lead to what we call collective intelligence.
Collective intelligence, so the whole becomes greater than the sum of its parts.
Exactly. It's a dynamic process that's closely linked to how well the individual agents develop and interact with each other.
So we've talked about evaluating the performance of a single AI, but how do you even begin to assess a whole team of them? It seems like that would be much more complex.
It definitely is. It requires a real shift in our thinking about evaluation. Instead of just looking at how well each agent performs on its own, we need to look at how they interact, how well they plan together, how effectively they communicate.
So it's not just individual performance, it's team performance.
Exactly. And our sources discuss benchmarks for evaluating MAS on tasks like code reasoning and knowledge reasoning, mentioning systems like master and reflection. But beyond these specific tasks, there's a real need for more holistic evaluation, looking at things like how well they collaborate, how efficient they are as a team, the quality of their decisions, and how flexible they are in different situations, both when they're working together and when they might be competing.
Makes sense. It's like evaluating a sports team. You have to look at how they play together, not just individual stats.
Exactly. And one of the biggest challenges with MAS is scalability.
Scalability, right. What are the issues there?
As you add more and more agents to a system, the amount of communication needed and the potential for bottlenecks in coordination can just explode.
It's like trying to organize a huge party. It can get chaotic quickly.
Right. And to address this, our sources talk about different architectural approaches, like centralized systems, decentralized systems, and hybrid models that combine elements of both. They also mention techniques for optimizing the network of interactions and reducing communication overhead, things like graph search, reinforcement learning to update communication strategies, evolutionary methods to refine the network structure, intelligent filtering of messages, and asynchronous communication where agents don't have to wait for each other to respond before acting.
So many different ways to try to manage the complexity.
It's a very active area of research, trying
Yeah.
to find the most efficient ways to get large numbers of agents to work together effectively.
Okay, so this all sounds incredibly powerful. The potential is huge, but it also raises some serious questions about making sure these agents are safe and beneficial. What are the main concerns in this area?
Safety is absolutely crucial, and our sources break down the risks into two main categories. Agent intrinsic safety, which are problems within the AI itself, and agent extrinsic safety, which are risks that come from how they interact with the world around them.
Okay, so internal and external risks.
Exactly. And when it comes to intrinsic safety, one of the biggest concerns is with the AI's brain, the large language model at its core. These models are vulnerable to things like jailbreaking.
Jailbreaking like with a phone.
Yeah, kind of. It's where people try to trick the model into doing things it's not supposed to do.
Oh, okay.
And prompt injection, where malicious instructions are hidden within seemingly harmless inputs.
That sounds tricky. And are there different types of these attacks?
Yes, our sources talk about white box attacks, where the attacker has knowledge of the model's internal workings, and black box attacks, which only rely on observing the inputs and outputs. There are also data poisoning attacks, where malicious data is used to corrupt the training process, and backdoor injection, where hidden triggers can cause the model to behave unexpectedly.
So they're finding all these clever ways to manipulate the AI.
Unfortunately, they are. And then there are privacy risks as well, like membership inference attacks, where someone tries to figure out if specific data was used to train the model, and data extraction attacks, where they try to steal information from the model itself.
Wow, so it's like a constant arms race trying to stay ahead of these threats.
It really is. And it's not just about the AI's brain, it's also about the other parts of the agent, like how it perceives and acts.
Right, so what about those non-brain modules?
When it comes to perception, there are threats like adversarial attacks, which can subtly alter sensory inputs to trick the agent, and issues with misperception due to things like sensor noise, objects being partially hidden, or limitations in the AI model itself. And in the action system, there are risks related to the tools agents use, such as supply chain attacks where the tools themselves might be compromised, and general safety concerns about how these tools are used.
So it's like any complex system, there are multiple points of potential failure.
Exactly. And then there are the extrinsic safety risks, which come from how agents interact with the outside world and with each other. For example, how agents interact with their memory could lead to corruption of that memory over time. Their actions in the environment could have unintended and potentially harmful consequences. And in multi-agent systems, there's the potential for agents to exhibit adversarial behavior towards each other.
So it's not just about making sure the individual agents are safe, it's about making sure the whole system is safe.
Exactly. It's a systems-level challenge.
And finally, our sources mention these concepts of superalignment and a safety scaling law. What are those all about?
Superalignment is a really important idea that focuses on ensuring that highly advanced AI systems remain aligned with human goals and values, even as they become much more capable than current systems. It goes beyond traditional safety measures and aims for a deeper, more robust alignment.
So it's not just about preventing harm, it's about making sure they're actually beneficial.
Right. And the safety scaling law, as illustrated in Figure 21.1, looks at the relationship between the capabilities of an AI model and how vulnerable it is to attacks. It suggests that as AI becomes more powerful, ensuring its safety becomes even more crucial and potentially more difficult.
It's like the more powerful something is, the more careful we need to be with it.
Exactly. And that highlights the ongoing challenge of finding the right balance between capability and safety.
This has been a truly fascinating deep dive into the world of AI agents. To recap, it sounds like these systems are rapidly evolving, drawing inspiration from our own brains, learning and improving in incredibly complex ways, collaborating to solve incredibly difficult problems, and facing some very real safety considerations that we need to address head on.
I completely agree. And for you, the listener, understanding these fundamental components, the ways these agents evolve, their incredible potential for collaboration, and those absolutely crucial safety issues, it all provides a really solid foundation for understanding and navigating the future of AI. It's a rapidly changing landscape, and staying informed is more important than ever.
So as these intelligent agents become more and more integrated into our world, here's a final thought for you to consider. How do we best balance their ever-growing capabilities with the absolute need for strong safety measures and ethical guidelines? How to make sure that these powerful technologies are used for good, that they truly serve humanity's best interests? It feels like this is an ongoing journey of discovery, not just for AI, but for all of us. Thanks for joining us on the Deep Dive.
Thanks for having me.
It's been great.
It's been a pleasure.